Thank you very much. It's my pleasure to speak at this symposium in honor of Professor Stathopoulos. And I must apologize for the title of my talk, which is completely outside the scope of the symposium. But I hope that you will be enjoying yourself during the presentation. It's about vortices meeting solid structures. And this is a bit a fundamental problem, but it's also met in certain cases, like in the built environment. So in that sense, I think my talk might even fit in this symposium. I'm showing you here a classical behavior of a vortex dipole, that's approaching a solid wall. There is a wall on the right of each panel. The dipole consists of two halves. It propels itself, it's going from left to right, and it meets the wall. And this is an inviscid simulation. And you can see that when it approaches the wall, it splits, and each half moves along the wall. That's due to its mirror image on the other side of the wall. This is a classical, unrealistic case, without any viscosity. If you turn on viscosity, things become different. You can see the dipole approaches the wall, but now boundary layers are formed. We are looking at vorticity here. So each vortex induces a boundary layer with opposite vorticity. That opposite vorticity is peeled off, and you can see the generation of secondary dipoles. And they are asymmetric, they curve backwards, and then they may even hit the wall again. And this may happen again and again. And this is the picture that you should keep in mind when you're sitting in an airplane. An airplane, when it lands or when it leaves, it produces wingtip vortices, and they propel downwards, and they meet the floor. And the classical picture that people had was this. So these vortices will move away, and if you wait 1 minute, then they're gone. But this is what happens. So the vortices remain in the strip area where the plane has landed or where it's taking off. So it's a complicated behavior, and it's all due to this no-slip condition at the wall that leads to a boundary layer. Well, this was nicely visualized in an experiment that I did a long time ago. This is the numerical simulation, and this is a dye visualization, and you can see that the correspondence is quite remarkable. If you go to higher Reynolds numbers, and that's something we did a few years ago, then it turns out that there are many, many small-scale structures in the boundary layer at the wall. So it's much more complicated than the picture that we have just been seeing. Now you can ask yourself the question, what happens when a vortex doesn't meet a flat wall, but it meets a wall with a sharp dent, or let's say a wall with a sharp edge. And a sharp edge might induce a singularity, so the velocities according to the model become infinitely large, which is physically not realistic. So something must happen there in order to make a good model. And in aerodynamics, the Kuta condition has been introduced in order to remove the singularity at sharp edges. So now the question is, how will a vortex behave when it meets a sharp edge, like the corner of a building or another sharp edge of a solid obstacle? Well, there is a classical approach, and this is just one example of a paper in which this classical approach was taken. This was the flow between two plates with sharp edges. And these people considered dipoles, so here you can see one point vortex, here another point vortex, and these point vortices would move along a straight line. And when they're close enough, they get through the gap. When they are larger than this distance, for example here and there, then they would split, and they would follow the solid plates. And there is a critical distance where they would, well, be on a kind of special trajectory. And if they would be released here and there, they would just follow the plates. That was the classical point vortex model. Well, some other studies have been done, and the idea is that this geometry is mapped by a conformal mapping, by Schwarz-Christoffel mapping, so that you can easily solve the problem in the mapped plane with very simple analytical means. But the idea is that the point vortex will always move along that sharp edge, for example here or there. Well, we have studied that sharp edge again, but since the sharp edge always introduces a singularity that people here didn't care about, I mean the singularities at the corners were just ignored. Well, and it's physically not realistic. So we decided to find a very, well, elegant way, simple way to model this, to remove this singularity at the sharp edge. Well, the idea is the following. We consider a point vortex dipole that's moving downwards in this picture towards the plate here. And we applied a conformal mapping. So we mapped this to a plane in which we in fact opened up the wedge to a half plane. And then it's easy to introduce a mirror vortex in order to represent the plane. And what we did is we introduced a Kuta vortex. That's an additional point vortex that was positioned close to the sharp edge in such a way that its strength was adjusted in such a way that it removed the singularity at the corner. So it's just like the Kuta condition in aerofoil theory. And the idea is that every time step you adjust the strength of that Kuta vortex in order to remove the singularity, in order to make the velocity regular here. That was the whole trick that we applied. Well, there are some parameters, but we kept most of them fixed, and I will only talk now about the parameter x0, which is the offset with respect to the sharp edge. And the rest of the parameters is fixed in the pictures that you see here. Well, this is a typical result. 1 and 2 are the point vortices at time t is 0. And the dots indicate the positions each time step further. And you can see that when it meets the wall, it splits up. It's an inviscid model. So the right-hand one is going to the right, following the wall, due to its image. The other one, due to its image, moves to the left. But then the Kuta vortex becomes active. And it becomes active in order to remove the singularity at the sharp edge. And here you can see how its strength had to be adjusted in order to satisfy the Kuta condition. And now we introduced the following rule. If its strength was reaching a certain value, comparable to the values of the original point vortices, it was released. So it could flow away at will. And that happened at some stage when the other vortex was coming along. It built up the strength, and then it was released, and they together went off as a kind of dipole. Well, and if you change the offset a bit, you can see different trajectories. But in all cases, it's obvious that this Kuta vortex played an important role. So you can see that the dipole splits up into one single vortex moving along the wall, and a dipole was formed once of the original point vortices pairing up with the Kuta vortex. And even if you make the offset larger, you can see the effect of the sharp edge in terms of producing vortices. And in this case, even 2 Kuta vortices. Well, this is maybe a bad recording, but it's an experiment showing a dipole vortex coming from left to right. Over here we have a sharp-edged plate. We added some dye in order to visualize the flow. And you can see that the dipole, the original dipole, splits up. And the upper half in the picture pairs with what is seen here as a Kuta vortex, and indeed leads to a dipole. The lower part behaves different from the simulation that we just saw, because we have a no-slip boundary condition at the wall. So there is secondary vorticity formed, leading in fact to this lobe pairing together with the original vortex into a dipole. Well, and if you introduce a contour with tracer particles inside, the point vortex model shows you nicely how the contour is affected. So it shows you nicely how dye in the experiment, if you wish, is affected. Well, and this is not very different from what we saw in the experiment. This is a numerical simulation. Here is the sharp-edged plate, and you can see that even although the distance from the plate is large, the plate is becoming active in the sense that it produces a vortex, and there is some additional vorticity produced afterwards. That's because of the flow introduced by the passing dipole. Well, and if you change the offset axis, then the effect is only more pronounced. So this is the Kuta vortex, and there is secondary vorticity formed in the boundary layer. This is a no-slip condition. So you can see how important this sharp edge is in producing vorticity. So it's determining, to a large extent, the behavior of the point vortex when it's getting close to the sharp edge. Well, we also did another experiment, an opening between two plates, and we had rounded edges in order to make it numerically somewhat easier. The dipole is coming from the left, and we introduced a few non-dimensional numbers, but the most important one for now is B, which is the ratio of the gap width versus the diameter of the dipole. Well, and this is a set of pictures showing what happens. The dipole was originally in the circle, it's moving from left to right. The gap is rather narrow, and you can see that it doesn't get through. Second attempt, doesn't get through. If you, well, this is in a nutshell what we just saw. And now if you increase the ratio B, so you make the gap somewhat wider, then you can see that it still doesn't get through at the first attempt, but then we see the bouncing, and then the secondary dipole is formed that's now approaching the gap, and indeed that is able to pass through it. So not the first attempt, but the second attempt was successful. And that's what you see here in this sequence. Well, if you increase the gap width, then it's obvious that the dipole gets through, but even then you can see the effect of the edges of the plates. Well, variation was a set of cylinders that were put on a row, and you can put them together, or you can leave a little opening so that you have a kind of model of a porous wall, which was what we had in mind. And it turns out to be a rather complicated business because of all these little cylinders and openings in between. A lot of vorticity is produced on small scales. This is just another example of a dipole hitting a set of cylinders with an opening between them. We decided, because it's so complicated, to look at a single cylinder. So a dipole hitting a cylinder that could be either rotating or non-rotating. This is what happens if you would have a dipole that hits a cylinder, and the cylinder is indicated by the circle here. And again you see secondary vorticity generated, leading to a dipole splitting to new dipoles. And even if you make the cylinder very, very thin, it could be just like a thread, it generates a secondary vorticity. That's because of its enormous curvature effect. And this is an experiment, and well, as a comparison we see the numerical simulations visualized by red and blue, the vorticity, and this is just a paint showing us essentially the same. Now it's hitting a smaller cylinder, and you can see how the secondary vorticity is formed. Here there is no die, but essentially doing what the numerical simulation also clearly shows. Now we did another experiment on a rotating cylinder. So this is all in a rotating fluid, but that's not important. We use the rotation in order to make the motion 2D. There is a dipole generated, and it's coming in this direction, and it's hitting the cylinder here that's rotating as a whole. Rotating cylinder implies that there is a boundary layer around that cylinder. It's rotating in positive sense, so the boundary layer has negative vorticity. This is positive vorticity, negative vorticity. Well, look at what happens. It breaks the symmetry of the collision, and you can see that undyed fluid originating from that cylinder area has negative vorticity and pairs with one half of the dipole, while the other one is just wrapped around the cylinder. So you can see that this symmetry breaking causes a completely different behavior of the dipole. In a numerical simulation, we saw the following. Well, in this case the cylinder is rotating in the opposite direction, but the structure is essentially doing the same. So the dipole went towards the cylinder and was distorted quite heavily, but look at this red patch, that oval patch. It looks like the great red spot of the planet Jupiter that also survives. So apparently there is a elliptical vortex region that survives in the shear flow generated by the rotating cylinder. So an intriguing behavior showing that the asymmetry caused by the rotation of the cylinder is really causing well, a dramatic effect on the behavior of the vortex. In order to better understand it, we removed the curvature. This is just a sliding wall, and the wall was sliding vertically upwards, and the dipole comes from left to right. And of course there is a boundary layer. Red means positive vorticity. And you can see how the dipole reacts, and you can see an asymmetry in the rebound of each half of the dipole. And well, it's obvious that this one is completely different from that one, due to the asymmetry in the vorticity present at the wall. So you can see it collides, and then you see an asymmetry in the collision. This is maybe relevant for the case of the wingtip vortices behind an airplane when there is side wind. I mean, that's the same as having a sliding wall. There is vorticity on the ground, comparable to the vorticity that we see here. Well, this is what I would like to show you. The message is that walls and sharp edges play an important, very dynamical role in the sense that they are sources of vorticity, and they can affect the primary structures to a large extent. And still a lot is unknown, and well, it means that a lot of work still has to be done. I hope that although this topic was a bit maybe not in the core of the symposium topic, I hope that you have been well entertained by this. Thank you for your attention.